It's important to understand the basic functions of each piece of equipment in the studio. But the thing that is really important is how all of the equipment works together to create different styles of mixes. That is, how all the equipment works together to create good mixes, rather, great mixes. We will then have a framework for the discussion of different values for different types of mixes. Then we can have some really good arguments. We'll actually have something to argue about. In this video, we will explain the basic functions of all of the equipment in the studio. Using visuals of sounds, we will explain the most common parameters found in each piece of equipment. This video is an introduction to the basic functions of equipment. The idea is to explain each piece of equipment visually, so that in the next video, we can use these visuals to show different types of mixes. We will go into more detail on each piece of equipment in future videos. In order to make the huge variety of studio equipment fathomable, let's categorize all of the equipment based on its function in the recording process. Sound creators create sound. These include acoustic to electric instruments, from vocals to synthesizer. Sound routers route sound from one place to another. Mixing boards route the signal to 4 places: the multitrack, the speakers, the headphones for the band out in the studio, and the effects so we can have a good time. Patch bays are just the back of everything in the studio next to each other. It's the back of the mix panels, the back of the multitrack ins and outs, back of the console ins and outs, and back of the effects ins and outs. It's the back of everything next to each other so we can use short cables to connect everything in the studio. Sound storers store sound. Tape players store digital or analog sound. Sequencers store MIDI information. Sound transducers are equipment that take one form of energy and change it into another form of energy. Microphones take mechanical energy or sound waves and change them into electrical energy. Speakers take electrical energy and change them into mechanical energy or sound waves. But it is sound manipulators that we are here for. This includes effects and processing that are used to change or add to a sound after it has been created. Now, there are only 3 components to sound: volume or amplitude, frequency, and time. That's all she wrote. Every single sound in the world can be described fully and completely by these 3 components. Therefore, every piece of equipment in the studio controls one or more of these 3 parameters. Here's a chart showing all the sound manipulators in the studio. Volume of the faders is shown as a function of front to back. Frequency is shown as a function of up and down. Time is shown in real time. That is, when a sound occurs, the visual representing that sound will appear and flash. In the first video of the series, we showed how we mapped out volume as a function of front to back. As previously mentioned, we can use volume faders to place a sound out front, in the background, or anywhere in between. In the next video, we will cover how volume relationships can be used to create different musical dynamics.
When we set volume relationships in a mix, we use apparent volumes to decide on the relative balance, not just the voltage of the signals going through the fader. If we were just using where the faders are set relative to each other, then we could mix without even listening. We could look at the faders and place them based on their relative placement, like this. When we raise the faders on the board, we are changing the voltage of the signal being sent to the amp, which boosts the wattage, which then sends more power to the speakers, which create more sound pressure level in the air that our ears hear. However, there's more to it than that. The other main thing that affects apparent volume is the waveform of the sound itself. For example, A chainsaw will sound louder than a flute when they're both exactly the same volume on the VU meters. A screaming electric guitar sounds louder than a clean guitar sound, even if they're both at exactly the same volume.
So when you see sounds represented by spheres between the speakers, you're seeing the apparent volume of a sound. This is what we use to mix with. This is what we use to set volume relationships. You don't look at the faders, you listen for the relative volumes.
Bass, come down.
Also, as previously mentioned in the first video, panning is naturally mapped out as left to right. If we think of the space between the speakers as a palette on which to place instruments left to right, we are free to pan as we please. However, particular styles of music seem to have developed a tradition for placement of particular instruments left to right in the stereo field. Obviously, movement of a pan pot during a mix creates an especially effective dynamic. We will discuss the common ways that panning is used to create musical dynamics in the next video. Compressor limiters are volume functions. Their main purpose is to turn the volume down. Compressor limiters turn the volume down when the volume goes above a certain threshold. When the volume is below a certain threshold, the compressor limiter does nothing unless broken or cheap. The two main functions of a compressor limiter are: one, to get less noise on tape, a better signal-to-noise ratio. This is accomplished by compressing the signal on the way to the multitrack. And two, to stabilize the sound between the speakers. The first function, to get less hiss from tape, is the original reason that compressor limiters were first introduced into the studio. Let me explain it this way. Say I'm humming along at a low volume, then all of a sudden it gets really loud. Do-do-do-do-do-do-do. Well, the problem is, unless we turn down the fader, we're going to get distortion. And you can't have distortion. Get distortion, go to jail. So, you turn the volume down. But then, the low volume humming barely moves the needles on the tape player. And as you know, if the needles barely move, you hear as much tape noise as you do signal. It's called a bad signal-to-noise ratio, and it kind of sounds like shh. So, you turn down the peaks and then raise the overall volume above the noise on the tape, getting less hiss. The second function of a compressor limiter is to stabilize the image of the sound between the speakers. Check it out. When a bunch of sounds are bouncing up and down like VU meters, it can get to be extremely chaotic. But if we stabilize one of the sounds, it's easier to focus on it. Therefore, it seems more present just because our mind can focus on it. It's more stable. Now, if you stabilize all of the sounds in the mix, the whole mix will seem more present or clearer.
There are two main things that determine how much you compress. The more instruments and the more notes you have in a mix, the more you compress because the mix gets too chaotic or busy. The second thing that determines the amount of compression is the style of music. Certain types of music, such as pop, are commonly more compressed.
Now, after you stabilize the sound between the speakers, if you then turn up the overall volume, you can put the whole sound right in your face. This is commonly done in radio and TV commercials, which makes it sound louder, making it jump out and grab your attention. This might be annoying in radio and TV commercials, but it's great for a lead guitar or other lead instrument. If you want a lead sound right in your face, compress the hell out of it and turn it up. It also works when putting sounds in the background. The problem is that low volume sounds can easily be lost in the mix. They can be masked by other sounds in the mix, especially if the volume of the sound fluctuates. Let me demonstrate. If you have a sound in the background, sometimes you can't quite hear it that well, especially if it fades out. But then it comes back in sometimes, you hear the sound, then other times it goes out and you hear another sound. But if you compress it, you can hear every word they're saying, even if you're whispering, and it never fades out. If you don't compress it, sometimes you really don't know what they're talking about. Other times, you really do know what they're talking about. So you see, if you have a low volume sound and you put it in the background, if you compress the hell out of it, you can set it down low and still never lose it in the mix. It's always there because it's stable. There are two main knobs on compressor limiters, commonly called threshold and ratio. Visuals are especially effective in explaining what threshold and ratio do. If volume is shown as a function of front to back, the sphere is bouncing back and forth like a VU meter. It will then come out and smash into the threshold and stop if it's a limiter. The difference between a compressor and a limiter is that a limiter stops the volume from getting any louder than the threshold itself. A compressor, on the other hand, allows the volume to get a bit louder based on a ratio or percentage. Check it out. If we set the ratio to 2 to 1, it will go this far. If we set the ratio to 10 to 1, it will only go this far past the threshold. A good starting point is to set the ratio to 4 to 1. This is so that it turns the volume down without squashing. A squash sound sounds like this. The truth of the matter is you can set the ratio wherever you like. But also true is the fact that most people who are just starting out can't hear the difference between ratio settings very well. Until you can tell, 4 to 1 is a good place to start. Now this is how you set the threshold. The thing is, you don't look at the threshold knob. Well, you have to look at it for a second in order to get your hand on it. Then you look at the gain reduction meters, which show how much the compressor is turning the volume down. You turn the threshold knob until you get a maximum of 6 dB of gain reduction, regardless of the ratio setting. For some instruments like lead guitar or screamer type vocals, you can set the maximum level at 10 dB of gain reduction. These are the levels you can set it at so that you turn the volume down some without squashing it. Once you hear compression really well, set it the way you want. Until then, try setting the ratio at 4 to 1 and setting the threshold for 6 dB of gain reduction. Like compressor limiters, the function of a noise gate is to turn the volume down. Therefore, compressor limiters and noise gates are often packaged together in one box. The difference is that noise gates turn the volume down when the volume falls below the threshold. Noise gates have three main functions: to get rid of noise, to get rid of bleed, and to shorten the duration of a sound. One function of a noise gate is to put it on a guitar amp to get rid of amp noise when the guitar is not playing. You know, if you set a guitar amp up with major distortion and turn it up to 11, The amp makes a really loud when it's not being played. If a song were to end with a guitar solo, it might sound like this. Now, if we set the threshold correctly, it will sound like this. This is especially helpful in the middle of the song so you don't hear the amp noise. The threshold of the noise gate is set so that as soon as the volume fades enough to hear the amp noise, it gets cut off. Be careful, of course, not to cut off any of the guitar sound. Another common use of a noise gate is to get rid of bleed from other instruments in the room. Gates can be especially effective on drums to isolate each drum. And it's especially important on a snare when you've got a lot of reverb on the snare. Check it out. When volume is shown as front to back and the volume falls below the threshold, the sound will disappear. Noise gates can also be used to shorten the duration of a sound. This can make a sound shorter, which can be used as a quite bizarre effect. The threshold on a noise gate should be set so that it cuts the noise or bleed, but doesn't cut the main signal. Before we continue, I should remind you that we're just giving an overview of the functions of each piece of equipment in the studio at this point. The idea is to explain each piece of equipment visually so that in the next video we can use these visuals to show different types of mixes. We'll then go into more detail on each piece of equipment in future videos. As you can well guess, we could do a whole video on EQ alone, and we will. We'll begin our discussion of EQ by covering the differences between types of equalizers. Next, we'll explore all of the different frequency ranges between 20 and 20,000 hertz.
What about the other ones, the higher ones?
EQ is a change in the volume of specific frequency ranges of a sound. It's the same as the tone controls on a normal stereo, bass and treble. Now, there are three main types of EQ found in the studio: graphics, parametrics, and roll-offs, high-pass and low-pass filters. You all know what a graphic EQ looks like. It has a volume control for each frequency. You can turn a frequency up or down using the volume sliders. Visually, we'll show frequency as a function of up and down, so we have low to high frequencies here. We're showing the volume of a particular frequency as the brightness in that band. For example, if you turned up the highs around 5,000 hertz, you would see it get brighter in that frequency range like this. On a graphic EQ, you choose which frequency you will turn up or down by putting your finger on the correct slider. On a parametric EQ, you turn the frequency sweep knob in order to select the frequency that you want to turn up or down. Besides a sweep knob, a parametric also has a bandwidth knob, which controls the range of frequencies that are to be turned up or down. On a graphic EQ, when you choose a particular frequency to turn up or down, you're actually turning up or down a range of frequencies preset by the manufacturer. Engineers, being the control freaks they are, want to be able to control the range of frequencies they are turning up or down. With a parametric, the bandwidth knob gives you this control over how wide the frequency range is. The knob's usually called Q because they couldn't get the word bandwidth on the knob. A thin bandwidth is normally labeled with a peak, whereas a wide bandwidth is often labeled with a hump. Sometimes ranges of musical octaves are also used. For example, 3/10 of an octave to 3 octaves. The obvious advantage of a parametric is the control you have over the bandwidth. If a parametric doesn't have a bandwidth knob, it isn't a full parametric, unless you're a salesperson in a music store. These days, many manufacturers are using the term parametric to refer to a paragraphic or semi-parametric, which has no bandwidth control. Those bandwidth controls are expensive. Roll-offs roll off low or high frequencies. They are commonly found on major consoles as high-pass and low-pass filters, and on smaller consoles as switches. A high-pass filter rolls off the low frequencies and does nothing to the highs. It passes them. It only rolls off the lows. This is especially helpful to get rid of low-frequency sounds such as trains, planes, trucks, air conditioners, earthquakes, or bleed from bass guitar or kick drum, and serious foot stomping. Low-pass filters roll off high frequencies like this. These are especially helpful for getting rid of hiss. Roll-offs can often be found on microphones and smaller mixing consoles like Mackie and Soundcraft as switches that simply roll off lows when the switch is engaged. It is important to get to know all of the frequencies of sound by name. You see, the truth of the matter is that we know all of the frequencies from 20 to 20,000 hertz by heart. Our entire system, our entire psyche was designed to perceive sound. Not only our ears, but every cell in our body is designed to perceive frequencies.
Here's a picture of a water molecule inside a cell of our skin, reacting to certain frequencies.
Actually, when we hear sound, every single molecule in our entire body is creating a pattern based on the sound coming in. This means that our entire body is perceiving sound, not just our ears. You see, we were born to hum, to sound that is. Our entire body and being was created to perceive sound. Therefore, we all know every single frequency by heart. We've been checking them all out since the womb. We know all frequencies and pitches intimately. The trick is to learn their names. We'll get into more detail on all of the frequency ranges and how to remember them in future videos. Then you'll be able to remember what boosting or cutting each frequency does to each instrument in the world.
Specialists don't seem to agree on how different frequencies affect us emotionally. Quite understandable because of the subjective nature of frequency perception. Psychologists to philosophers have written books about how sounds affect us emotionally, and how people have organized their ways of perceiving difference in frequency. Different frequencies do affect us differently, both physiologically and psychologically, not to mention spiritually. However, even more powerful than the way specific frequencies make us feel is the way that combinations of frequencies make us feel.
The truth of the matter is that each and every sound, except a pure tone, is made up of a combination of tones of different frequencies and different volumes. These harmonics or overtones account for the differences in why one sound sounds different from another, a sound's timbre. Different sounds have different harmonics in them, and more or less harmonics as well. The interesting thing about harmonics is that they are all mathematical multiples of each other, and each individual harmonic is a pure tone. Therefore, when we raise or lower the volume of one frequency or another, we're actually raising or lowering the volume of one or more of the harmonics in the sound. This accounts for why each sound responds to EQ differently. Once in the mix, sounds should be EQ'd so that they work well with each other. Sounds can be made to sound more similar to each other or more dissimilar. A lead instrument might be made to be more cutting and abrasive so it really grabs attention. An instrument might be given extra bass to make the song more danceable or just to excite the rap listener. There's an important technique that you might find helpful for checking the relative equalization of each sound in a mix. First, scan the high frequencies and check the relative brightness of all of the sounds in the entire song. Make sure that all of them are as bright as you want them. Often they should have a similar amount of brightness, but sometimes you want some sounds to be even brighter than others. Sometimes you might want them to be duller than others. Second, scan the mid-range frequencies and check for the relative volume of mid-range frequencies across all of the instruments. Mid-range frequencies kind of stick out when boosted a lot. Make sure that all of the instruments have the amount of mid-range frequencies in them that you want. Just like highs, often they should have a similar amount of mid-range frequencies. However, sometimes you want some sounds to stick out more and grab your attention. Third, scan the bass frequencies and check for the relative volume of bass in each sound that hangs out in the bass range. For example, check the relative amount of bass frequencies present in the kick drum compared to the amount of bass in the bass guitar. Check it out and make sure that it's the way you want it to be. This frequency range is the one that is most commonly missed when mixing an album or project. This has been an introduction to EQs and equalizations. Check out future videos for more detail. A delay stores a sound on a chip and then plays it back at whatever time you like. The delayed signal can also be fed back into the input to get the well-known sound of feedback or regeneration where the signal repeats. Just as you need to learn the details of the frequency spectrum, you must also get to know how each delay time feels. It's the type of feeling or emotion that different delay time ranges evoke that you use to remember differences in delay times. We can also use the relationship between delay time and distance in the studio to help us to get to know different delay times. Sound travels close to 1 foot per millisecond.
1,000 milliseconds equals 1 second.
That means for every 1 foot in the studio, you're adding 1 millisecond of delay time. Therefore, it's very easy to hear a delay between two mics set at different distances. We can show how different delay times look quite clearly. Here is 500 milliseconds. Here is 100 milliseconds of delay time. Here's 40 milliseconds. Now, when we have a delay time less than 30 milliseconds, an unusual thing happens. Our ear and brain are not quick enough to hear two sounds. Our ear perceives this quick of a delay time as one fat sound. This effect is one of the most important and useful for a recording engineer. Any instrument can be made into stereo with fattening. It can be used to fill out a mix so as to make it sound fuller. It can be used to make an otherwise wimpy sound fatter, fuller, and bigger. It can also make a sound more present so that it can be turned down in the mix but still be discernible. Now, if we pan the original dry signal to one side and the delay to the other side, the sound seems to be stretched between the speakers like this. Now, if we add feedback to a sound, the sound repeats itself like this. What's happening is the output of the delay, the echo, is being fed back into the input of the delay to be repeated again. Adding a delay to a sound is the same as adding another sound or instrument to the mix. Therefore, it will always tend to make the mix seem fuller because there are more sounds to occupy the limited space between the speakers. You normally add delays to a mix only if you have room for them. Therefore, you wouldn't add delays to a very busy mix with a lot of instruments and a lot of notes. The exception would be heavy metal, alternative rock, and some new age music. These styles of music are commonly mixed to create a wall of sound. Therefore, to add another sound to fill this space can be just awesome.
Yeah, Phil Spector.
Yeah, he created that wall of sound type mix.
Rules.
When the delay time is long enough to hear two sounds, then the delayed signal can be treated just like another track, another sound. Therefore, the volume and panning can be set any way that you see fit.
As sweet as any harmony, but you blinded me with science, and failed me in biology. Yeah.
If you set the delay time for less than 30 milliseconds and crank up the feedback, you get an effect called tubing.
Totally tubular.
If you then change the delay time, you get an effect that sounds like this. If we set a clock to change the delay time on its own, we get the effect commonly called flanging. Notice that as the delay time gets shorter, the pitch seems to rise. As the delay time gets longer, the pitch seems to fall. Now, if we set the width or depth so that the sweep of the delay time is not so wide like this, then we have the effect commonly called chorusing.
It's poetry in motion. She turned her tender eyes to me, as deep as any ocean, as sweet as any harmony. But you blinded me with science, and failed me in biology. Yeah.
If we set the delay time so that we are only sweeping between 0 and 1 milliseconds, we have the effect commonly called phasing.
It's poetry in motion. She turned her tender eyes to me, as deep as any ocean, as sweet as any harmony. But you blinded me with science, and failed me in biology. Yeah.
All of these effects, flanging, chorusing, and phasing, are just changing short delay times with lots of feedback or regeneration.
In 1957, Tony Fisher was doing an album when someone accidentally leaned on the reels of the tape player like this. The tape slowed down, and then when I got back up, it sped back up to normal speed like this. The band went, cool, let's put it on the record. The song, The Big Hurt, went to number 3 on the charts in 1957.
Now you can also change the speed or rate of the flange, like so. You could set the rate of the sweep to the tempo of the song, or you could set it so that it is rising on one chord and going down on another chord. Or you could even set it so that it rises on the first half of the verse and falls on the second half of the verse. Flanging is commonly used to create a more spacey type of mood in the mix, sometimes used to create an otherworldly effect. It's great for the underwater type of effect. Chorusing is commonly used to simulate the effect that you get when you have a chorus of people or a chorus of instruments. Phasing is a very subtle effect, so subtle that it's the kind of effect that when used at Grateful Dead concerts, the crowd often wonders if the effect is actually coming from inside their head.
I thought it was inside my head.
Each of these effects can be panned in various ways, like this. Each can also be brought out front with volume. And raised or lowered a little bit with EQ. We'll explore more details about these effects in future videos, including how they are commonly used in mixes for different styles of music. Reverb is made up of thousands and thousands of delay times. When you first hear a sound in a room, the sound continues traveling out at around 700 miles per hour and hits the walls, bounces back from the walls, all at different distances, and comes back to us as hundreds of delay times. All of these delay times wash together to make the sound we know as reverb. When we place reverb in a mix, it's just like we are placing the sound of a room between the speakers. Therefore, we'll show reverb visually as a room or cube between the speakers. There are certain parameters of control that are commonly found in reverb units. First, you can change the type of room. You can think of it as different types of rooms between the speakers like this: halls, rooms, chambers, and plate reverbs. You can also change reverb time, the duration of how long the reverb lasts. Long reverb time would look like this. A short reverb time would look like this. When a sound occurs, it takes a while for the sound to travel out and hit walls before you hear the reverb come back. This time of silence before the reverb begins is called pre-delay time. A really long pre-delay time would look like this.
It's poetry in motion. She turned her tender eyes to me, as deep as any ocean, as sweet as any harmony. But she blinded me with science, and failed me in biology. Yeah. It's poetry in motion. She turned her tender eyes to me, as deep as any ocean, as sweet as any harmony. But she blinded me with science, and failed me in biology. Yeah.
But a natural room, like an auditorium, has a short pre-delay time that would look like this.
It's poetry in motion. She turned her tender eyes to me, as deep as any ocean, as sweet as any harmony. But she blinded me with science, and failed me in biology. Yeah.
Another setting of reverb is the envelope. That is, how the reverb changes its volume over time. Normal reverb has an envelope that looks like this. Engineers, being the bored people they are, thought to put a noise gate on this natural reverb, which then chops it off. Therefore, the volume stays even, then stops abruptly, like this.
It's poetry in motion. She turned her tender eyes to me, as deep as any ocean, as sweet as any harmony. But she blinded me with science, and failed me in biology. Yeah. It's poetry in motion. She turned her tender eyes to me, as deep as any ocean, as sweet as any harmony. But she blinded me with science, and failed me in biology. Yeah.
Now, if we were to take the envelope of normal reverb and turn it around backwards, the volume of the reverb would rise, then stop abruptly, like this.
It's poetry in motion. She turned her tender eyes to me, as deep as any ocean, as sweet as any harmony. But she blinded me with science, and failed me in biology. Yeah. It's poetry in motion. She turned her tender eyes to me, as deep as any ocean, as sweet as any harmony. But she blinded me with science, and failed me in biology. Yeah.
Now, if we were to take the tape and play it backwards, it would sound like this. Now, if we put reverb on the vocal and record it on some open tracks, then turn the tape around to run forward, we'll get an effect like this.
That. So cool.
This effect is called preverb. It's the most evil effect that can be created in the studio because only the devil could put an effect on something before it even happens. Therefore, it has been used in every scary movie made, including The Exorcist and Poltergeist, and of course, it's Ozzy Osbourne's favorite effect. It can also be fun as hell, too. One of reverb's main functions is to connect sounds in a mix and fill in the space between the speakers, like this.
When she turned her eyes to me, as deep as any ocean, and sweet as any harmony. She's blinding me with science. She's blinding me with.
Like any sound, reverb can be panned in various ways, like this. Reverb can also be brought out front with volume, or placed in the background by turning down the volume. And it can be raised or lowered a little bit with EQ. We have covered volume changes, panning, EQ, compressor limiters, noise gates, delays, flanging, phasing,
As deep as any ocean,
chorusing,
it's poetry in motion.
and reverb.